This is SIDDHCESNA-II. It is a 16-bit CPU I designed from scratch. It features its own architecture, a language I named as Cessna, and a custom assembler. But before we look at the brain, we have to talk about the toy that started it all. In high-level languages, variables feels like they just exist. In hardware, we have to talk about registers. Think of RAM as a warehouse kilometers away. It is huge, but it takes too many clock cycles to get there. Registers are like CPU's pocket. They are fast but limited. In my CPU, I have exactly 4 general purpose registers, R0 through R3. Secret to SIDDHCESNA-II is the unified bus. Think of it as a highway connecting every part of the system. In most CPUs, math is a special complex command. In mine, math is just a move. Every component has a 3-bit ID. R0 is 000, the ALU is 100, and the display is 110. To this CPU, adding numbers is just moving data from the math ID to a register ID. Treating math as a data move across a highway keeps the architecture clean and predictable. Now let's look at the math logic. In chips like Intel or ARM, registers are connected directly to the ALU. I did things differently. I used 2 dedicated feeder registers, RA and RB. The add command is dumb because it only knows how to look at the feeders. This applies to all ALU instructions. I traded extra lines of code for a simpler hardware design with fewer transistors. It increases the clock cycle, but it makes the hardware logic much more transparent and easier to debug. How does the CPU know when to move this data? It's need a clock. It is not a clock that tells time, it's a heartbeat. It pulses 0101 constantly. Every pulse tells the program counter to move to the next line of code. Without this pulse, the electricity would just sit there. The clock turns it into a living process. I could not write raw binary all the time because I am a human, not a logic gate. So I wrote a custom assembler in C++. Takes my SSNA code and packs it into 16-bit instruction format. There was one problem in the original design. If I wanted the number 5, I had to manually fetch it from memory, which was slow. In the Pro version, I will try to implement immediate loads. This means I am carving out a space inside the instruction itself to carry the data. It makes the code denser and more efficient. Let's put it to the test by computing Fibonacci sequence. It is the hello world of the hardware because it tests loops, conditional jumps, the ALU at input out. Define the memory addresses, initialize the registers, and then enter the loop. If the condition is no longer met, the system halts. Now let's assemble it. Take this hex code and paste it into the SIDDHCESNA-II memory. We turn on the clock, and there is the Fibonacci sequence. Building SIDDHCESNA-II taught me that computing is not magic, it is just moving data at the right time. I am 14 while this version is complete and stable. The journey is not over. The source code is on GitHub via my website. If this video gets 4096 likes, I will start work on the Pro version. If you are into this kind of content, hit subscribe.